Welcome to the course Introduction to Molecular Thermodynamics. And in today's lecture, we are going to review the fundamental principles of classical thermodynamics. Now, the primary goal of classical thermodynamics is to study the equilibrium properties of a system. So, there is no thermodynamics, in thermodynamics there is no dynamics, and we are interested in time dependent properties of a system in equilibrium. So, the first question that arises is, what is a system in equilibrium? A system in equilibrium is something where the measurable properties are not changing with the system. Specifically, the goal of thermodynamics is determination of the equilibrium state that eventually results when a system undergoes a change in state. But why should we be interested in a change in state? You of course remember the famous story of James Watt watching a boiling kettle and how he observed that the steam could lift the lid of that boiling kettle. So, basically what we are looking for are different ways in which we are going to harvest energy from different sources and use it for our own benefit. So, these are the two primary goals which we try to attain in thermodynamics. And let me now go over and try to define schematically the typical way in which a change in state is visualized in the case of a thermodynamic process. First of all, let me have this initial equilibrium state. When you have an initial equilibrium state, you have prepared the system in such a way that if no external perturbation is provided, the system will be left as it is and its properties will not change with time. So, here we have one particular system that is contained in this box. It is surrounded by a rigid insulated wall and we have two compartments here. In the first compartment, as you see on the right, this is under high vacuum and there is say practically no molecules in there, and we have the other red compartment where we have put some gas, maybe some ideal gas, and this system, if not perturbed externally, will remain as it is. What we do next is we perturb this initial equilibrium state. As I said, there are two compartments here, one here, another one here, and there is a separator, as you can see over here. I am going to remove this separator, and when this separator is removed, what does the system face? It faces this kind of a situation where the gas is now faced with the choice of undergoing a change in state. Then the question that we ask is, what will happen when the system undergoes this change in state, or in other words, what is going to be the final equilibrium state as the system undergoes this change in state? From our experience, we know that this ideal gas is next going to fill up this entire box, and once it has filled up this entire box, it will not undergo any further change in state, and if I go on measuring its properties, it will be independent of time if no further external perturbation is provided. And this means that you have passed from an initial equilibrium state to a final equilibrium state. And the question that you ask is, during such a process, can I harvest energy for some useful purpose? Now, let us talk about the key features of classical thermodynamics. First, what is the system that we are talking about? I have already shown you some schematic diagram, but let me define in the most general terms what I mean by a system. It is a part of the universe whose properties are being investigated. Okay? So, it may be a box or a cylinder full of some kind of a gas. It may be a closed vessel full of some liquid that you are interested in, or it may be a block of solid. And the next one that we would like to talk about is what we mean by the surrounding of the system, because this also is very important in understanding the property of the system. So, since system is only a part of the universe, in most of the cases we assume the rest of the universe as the surrounding to the system. And we also must mention that the systems that we are interested in have macroscopic dimensions, by which I mean that if you have a block of solid, it will have a typical length of 1 meter, time of, and if you are looking at the time dependent property of such a system, it will be typically measured in seconds or a few tens of minutes or even a few hundreds of minutes, but the time scale over which you will be following the properties of the system will typically be in minutes. And then I must mention this very important, that the number of particles is going to be very large, and therefore, when a system is in equilibrium, when any such system is in equilibrium, you are basically trying to make an observation or the measurement of the system from time to time, let us say once every minute or maybe once every 10 minutes or so, and trying to measure some kind of property of that system that you are interested in. So, now I would like to highlight once more that I am talking in terms of a macroscopic property, a macroscopic system which is comprised of a very large number of particles, and the system is in equilibrium, and all my measurements are done typically within about a minute, and all properties of the system thus measured are independent of time. So, those are the properties that we are interested in when we are studying or describing a system using classical thermodynamics. Now, when we talk about the equilibrium properties of a macroscopic system, the fundamental statement of thermodynamics is that there exists a particular state that is called the equilibrium state of simple macroscopic systems that are completely characterized by only 3 variables. Now, this is probably the most important property of the entire subject area of thermodynamics. Think about it. You have typically Avogadro number of particles, and these particles are making up a block of the substance, which is something that I can see with the naked eyes. I can make measurements on it in the real world, and I am trying to describe the equilibrium state of the system in terms of just 3 variables, and that is probably why thermodynamics is so successful in describing such systems. Now, what are these 3 variables? To start with, the first quantity that we can talk about is the internal energy. The second one, volume, and the third, the number of particles. You may argue that why these 3? As we will see later, that these 3 variables actually give you a unique representation of the system, which is the simplest one, that is an isolated system, a system that is not interacting with the surrounding. You may also ask, if what happens if I have a multi-component system? In that case, instead of n, that is the number of particles of a single type, you are going to have different species So, species 1 will have the number of particles equal to n1, species 2 will have number of particles n2, and so on and so forth. So, with this in mind, that thermodynamics is actually giving us a very simple description of a very complicated situation, we next go and try to see how do we think of the system and its interaction with the surroundings. So, here we go. So, first let me point out that this is my system and this white portion is my surrounding. Now, the system is surrounded by a wall that is completely insulated, as a result of which it cannot exchange energy, volume or matter with its surrounding. And we would call such scenario as describing an isolated system. It may so happen that the wall is of such nature that it allows exchange of energy between the system and the surrounding. In that case, we call the system a closed system. Please note that the system is incapable of exchanging either volume or matter with the surrounding. And there is a third scenario where you have the system exchanging energy and matter across the wall, separating it from the surrounding. So, in that case, we will call such system an open system. So, thermodynamics tells us that there are different ways of monitoring the system and its interaction with the surrounding by varying the property of the wall that separates the system from its surrounding. So, take the isolated system. If I have an adiabatic wall that is rigid and impermeable to the substance that is there inside the box, I will be having an isolated system, isolated from the surrounding. And I can very easily describe the equilibrium state of the system by assigning specific values of its energy U, the volume of the box V, and the number of particles present in the system. On the other hand, when I have a closed system, I may design the wall to be diathermal, which means it allows exchange of energy between the system and the surrounding. If I keep this wall rigid and impermeable still, then what do you think would be a good description of the equilibrium state? Since the system can exchange energy with the surrounding, therefore, when the system attains an equilibrium, its temperature is going to be equal to the temperature of the surrounding, and this constant temperature is then a very good descriptor of the equilibrium state instead of its total energy. So, the equilibrium state under such condition will be described in terms of these three variables: T temperature, V volume, and N the number of particles. You may also think that, well, in addition to the diathermal wall, let me make at least one of the walls flexible so that the system can exchange volume with the surrounding. Of course, you can do it by attaching a piston, and in that case it is understandable that the equilibrium state will be described in terms of temperature, pressure, and the number of particles. And if you have an open system, you may still design the system with a rigid wall, but it may be diathermal and permeable. Let us say that it is a porous wall. In that case, the equilibrium state is going to be defined in terms of temperature, volume, and another system property which is known as the chemical potential. Now, when we go for understanding the interaction between the system and the surrounding, the next thing that becomes important is, if the system has interacted with its surrounding and attained an equilibrium state, In that case, what are the different kind of equilibrium states that we can think of? The first one that we can think of is the thermal equilibrium. So, this is the case where we have, let us say this is the system and this is the surrounding, and the system and the surrounding, they are exchanging energy as heat, and this wall is a diathermal wall or diathermic wall, and the system will go on exchanging energy with its surrounding till both the parts attain equal temperatures. Under such condition, I will say that the system and its surrounding are present in thermal equilibrium with each other. The next scenario that I will highlight over here is when the system is distinguished, when the system is separated from its surrounding by a movable wall, and I can move this in this direction if there is a high pressure in the system and a low pressure in the surrounding, then this will spontaneously move to this direction. And when will the motion of this movable wall stop? It will stop when on both sides of it, that is between the system and the surrounding, the pressures are equal. We would then say that the system has attained a mechanical equilibrium with its surrounding. The other scenario is generally known as material equilibrium or equilibrium with respect to matter flow. So, if I have a porous wall which is diathermal in nature as well, and if this system is maintained at a high temperature and the surrounding at a lower temperature, then there will be the transfer of heat from the higher temperature to lower temperature till the system and the surrounding acquire equal temperatures. In addition, if I make these walls porous, there will be transfer of matter from, let us say, the system to the surrounding, and this transfer will continue till the chemical potential is equal in both the system and the surrounding. So, these are the three types of equilibrium that we come across in the real world, and thermodynamics introduces us to the concept of giving a precise definition of how to get from experiments the condition of equilibrium under such circumstances. So, let us say that you have kept your system in contact with a thermal reservoir. So, this is a schematic representation where you have a system and you can vary the property of the wall surrounding the system to control its interaction with the reservoir. So, if this wall is diathermal, rigid and impermeable, then the reservoir can be taken as a thermostat. So, under this condition, as I have already mentioned, the equilibrium thermodynamic state of the system will be given by temperature, volume and the number of particles, and the condition of equilibrium is that the temperature of the system is equal to the temperature of the reservoir. On the other hand, a more common and system is where this wall is diathermal as well as flexible, but impermeable. In that case, this reservoir is going to act as a thermostat plus a barostat, and the thermodynamic state is going to be defined in terms of temperature, pressure and the number of particles, and then the condition of equilibrium will be that the temperature of the system is equal to the temperature of the reservoir, pressure of the system is equal to the pressure of the reservoir. And then we come across this very important concept of equation of state. So, what is the equation of state? This is a mathematical relationship between appropriate thermodynamic variables of a system at equilibrium. So, what I have here is something that is giving me interesting relationships. Why do I need them? I need them because I am interested in finding out how to handle these systems under different conditions. So, do I know of any example? Of course, you know. From your high school days, you have come across these equations of states for gases. The first one is the ideal gas equation of state. So, I am sure all of you have seen this equation, which connects the pressure, volume, temperature and the number of moles or the number of particles of the ideal gas for an equilibrium state. And this ideal gas equation of state also demonstrates the very fact that you require only 3 variables to define the equilibrium state of the gas. Have a look at this. Because of the existence of this kind of a mathematical relationship, you can always have n expressed as a function of P, V and T, or T expressed as a function of P, V and N, and so on and so forth. Therefore, you require only 3 variables to describe the equilibrium state of a system. Now, if I come to the van der Waals equation of state, this is something that has been obtained from experiments to describe the properties of real gases. And here also you see, because of the existence of this kind of an equation of state, you require only 3 variables to describe the properties of the system. In fact, what you have here is the existence of an equation of state under various conditions can give you a lot of information regarding what would be the predicted property of the state. If, for example, you are having an ideal gas and you can vary 3 variables independent of each other: pressure, volume and temperature, and this blue surface is showing you the way in which an equilibrium state will be defined in terms of these 3 variables. Therefore, from here you can project it in different directions and see, for example, how volume is going to vary as a function of temperature, or pressure is going to vary as a function of temperature, keeping the 3rd variable constant. Now, when we talk about thermodynamics, of course, I have already mentioned to you that we are interested in thermodynamic processes that take the system from one equilibrium state to a final equilibrium state. I would like to mention here all the points that you see in this surface that represents the equation of state for an ideal gas. These are equilibrium states because they obey, these points have been generated from the ideal gas equation. So, this equation, this point or this point, they represent equilibrium state of the ideal gas. And there may be a very large number of processes, and I am sure all of you know about these isothermal, isobaric, isochoric processes, which may be adiabatic processes, exothermic or endothermic processes, cyclic, reversible or irreversible processes. And what I would like to mention here is something that if you prepare a system in an initial state, so let us say that I have a cylinder which I have prepared in an initial state by putting a piston over here, and there is some weight holding the piston here, and there are some stops over here, and on this side of the piston we have some gas. Now, I can induce this system to undergo a change in state by withdrawing the stops. When I withdraw these stops, the system will equilibrate in a final state which looks like this. Okay? I have taken away the stops, I have taken away the mass, and the piston has moved, and this separation has got stopped at the position of these final braces over here. If I could carry out this process in a very slow manner, I would say that I am looking at a reversible process. And under such condition, if I come up with a pressure volume indicator diagram, this is my initial state, this is my final state, and since I have maintained equilibrium all throughout the process, all the points in this curve, they represent intermediate equilibrium states, and therefore, the PV indicator diagram includes all the states that have been covered in going from the initial state to the final state. But on the other hand, if I carried out this process very, very fast, I would have reached some other final state, but in this case it would be an irreversible change where the initial and the final states are the only two equilibrium states that I talk about. I did not allow the system enough time to equilibrate with its surrounding. And therefore, as you know already that under such circumstances, this is going to be the work done in this process, while in the reversible process we are going to have the area under this curve as the amount of work done during a reversible change. Now, this brings us to the laws of thermodynamics. Now, the laws of thermodynamics are quite well known to the students, that is what I will assume. So, I will give a quick look at what the first law of thermodynamics tell me. The first law of thermodynamics introduces to us an extensive state function, which I will represent as U and term as the internal energy. It says that this is a function, it undergoes a change in value delta U during a change in state, and delta U is equal to Q plus W, where Q is the heat exchanged and W is the work done during the change in state. So, when we know about the first law of thermodynamics, so basically we understand that the internal energy of a system can be changed in two different ways, either by transferring heat or by allowing the system to do work or by doing work on it. So, when heat is transferred to the system from the surrounding, usually the sign convention, that is Q is positive. So, it contributes to the increase in delta U, increase in the internal energy, and if heat is transferred from the system to the surrounding, U decreases. So, Q will be assigned a negative value. Similarly, if the system expands, it uses up its internal energy to do work against an external pressure. So, W, the work done by the system, decreases U and it is less than 0. And similarly, compression of system by an external pressure, that would be associated with increase in internal energy and W is greater than 0. So, this also says that I do not really have to have a finite process, I can also have an infinitesimal change, especially when I am talking about the reversible processes. So, for an infinitesimal change, du, that is the differential, exact differential of the state function u, this is a sum of two inexact differentials. This is the infinitesimal amount of heat exchanged between the system and the surrounding, and this is the infinitesimal amount of work done during the change in state that takes the system from a state having internal energy u to an internal energy u plus du. If you have an adiabatic process, then dq would be equal to 0. As a result, I will always have du is equal to dw. And for a cyclic process, the system comes back to the same initial state. So, the initial and the final states are the same. As a result, delta u, which is a state function, that would be equal to 0, which means that for every such process, q plus w is going to be equal to 0. And it is also understood from the first law of thermodynamics that the absolute magnitude of internal energy cannot be measured. Rather, when we study any thermodynamic process, we are measuring the change in internal energy. So, this now we can do in either a constant volume process where delta U is estimated as Q, and typically a calorimeter is used to estimate Q, or you can have an adiabatic process where delta U is measured in terms of the amount of work done during the process, and if it is a PV work, once again it can be measured. That brings us to the end of our discussion of the first law of thermodynamics. Now, we know what is an equilibrium state of a system. Also, we know how an initial equilibrium state can move over to some final equilibrium state by some kind of process, and you can design these processes depending on the different conditions, like an isothermal process, an adiabatic process, a reversible process, an irreversible process, and so on and so forth. And the first law of thermodynamics tells us that there is some function which we call the internal energy. This is the capability of one given system to do some external work, and therefore, this is the quantity that we are interested in. Now, U is a system property. If I have an isolated system, then U will have a finite value, and as long as I do not change the property of the system, it will remain fixed at its equilibrium value. Now, if I induce a change in state, U will change. So, what are the ways in which U can be changed? First law of thermodynamics tells us there are two ways in which you can change the internal energy of a given system. One is the supplying some heat to it or extracting some heat from the system, or by doing some work either by the system or on the system. And this tells us that interaction of the system with its surrounding is possible only when the system is undergoing a change in state. But first law of thermodynamics does not tell you if a system will go in a particular direction. So, that is when the second law of thermodynamics comes into the picture, and we are going to talk about the first law as well as the second law of thermodynamics in characterizing the macroscopic systems in our next lecture. Thank you.